Recording in progress. Okay. I'm going to be going through the first page of the closure, hopefully front and back, and then there'll probably be a second video for that second page. One thing that I want to note is that all of these that have a little asterisk, you would be able to use your calculator. Those that don't, you'd be expected to just use your assessment resource page, and mostly, more specifically, the unit circle on its own will be able to help you with them. So to start all of these, you have your calculator for. When I want to convert from radians to degrees or vice versa, in this case, angles to radians, on your assessment resource page, you're going to have that information that pi radians is equal to 180 degrees. Now, that's not that helpful unless you know which one goes on top of that fraction when you multiply. So since I want to make this into a radian, I'm going to want my radian to be on top when I multiply. So I'm going to multiply by pi over 180. At this point, I've got 22 or 225 pi divided by 180. You always simplify the fraction if you can. You'd have your calculator for this part. Dividing both of those by 45 gives us 5 pi over 4. And that's our final answer for that. Same idea, 75 degrees, making that into a radian, I would multiply by pi over 180. That gives me 75 pi over 180. If I can simplify the numbers, I should. So doing 75 divided by 100 in your calculator or knowing how to simplify it gives us 25 pi over 36. And that would be our final answer. Just because it's a negative degree, that doesn't really change our process. I'm still going from degrees to radians. So I still multiply by pi over 180. At this point, I just have negative 15 pi over 180, and I simplify it in the same way. I can divide both of those by 15, and that just gets me to negative pi over 12. The last one, the process does not change. Going from degrees to radians, you'd multiply by pi over 180. And then having 330 pi divided by 180, I can still simplify these numbers down, and that ends up being 11 pi over 6. Now, this one's also on the unit circle. So if you catch that and you see that it's 330 pi and you know that 330 pi on the unit circle exists, then you would automatically be able to say it's 11 pi over 6. If you didn't catch that, that's fine. You still have that process to go through. Okay, going from angles to exact degrees means I pretty much do the same thing, but flip that fraction around. Because I want to go into a degree, I want to make it into a degree, then my degree is the one that goes on top, that 180. So this time I would multiply by 180 divided by pi. Now what happens when the pi is on the bottom is that I have 1 pi on top, 1 pi on bottom, and they completely go away, which is good because I want to make this into a degree, meaning pi should no longer be in my answer. What's left is just 3 times the 180 on top and then divided by 11. So plug that in. It should give you 49.09 degrees. Rounding to 2 decimal places is a good rule of thumb. Just keep that in mind. This next one, 4 pi over 5. I want my degree to be on top, so I'm going to multiply by 180 over pi. Again, degrees on top because I want to make it into a degree. Pi and pi go away, which is good because then we're left with 4 times 180 divided by 5. That should give you 144. Don't forget the degree symbol. This last one is at 4 pi, so same idea, multiply by 180 divided by pi. I know that I want it to be a degree, so I want that pi to go away. Pi on top, pi on bottom, completely disappear. If you'd like to put a 1 under this 4 pi to just kind of keep things consistent, you can. But same idea, pi and pi go away. Now you're left with 4 times 180 divided by 1. Dividing by 1 doesn't do much, but we could still put it there. That gives us 720 degrees. I'll circle that last one. So just making sure you know when you're multiplying by this fraction, it's nice that we'll have this on the assessment resource page. You just have to know which one to put on top. Remember that whatever I want to make it into is the one that I put on the top. If I'm making it into a radian, then I want pi to be on top. If I'm making it into a degree, then I would want the degrees to be on top. All right, these next few have us sketching the different angles on a specific unit circle. So A says sketch an angle that has a positive cosine and a negative sine. I just want to point out that on the unit circle, coordinates look like x comma y, but x relates to cosine and y relates to sine. That'll be helpful throughout the closure. So if I'm creating a positive cosine, that really just means a positive x value. Well, where are the x's positive? Pretty much pretend that this right here is 0, 0, and left or right are my x values. Well, if I'm starting at 0, 0, anytime I go left, I'm feeding into the negatives. That means if I want it to be positive, then I really can only go somewhere over here. So far, I know that this is what is going to be involved. As for that negative sign, sine relates to the y values. So I'm anywhere over here for a positive x, but in order to have a negative sine value, I want you to think about this. Going up would mean positive, going down would mean negative. So although I'm living in this world over here for that positive cosine, in order to get to the negative sign, I'd have to go down. So really anywhere along this quadrant would really work. I'm going to put our point here on the circle. And how would I get there? Well, remember that the unit circle works counterclockwise. So if I'm starting at 0 degrees, I'd have to work all the way around in order to get there. So I'm just kind of going to make a mark that tells me I'm going to start here and work all the way around in order to get there. And this right here in blue is a theta or a degree. Now, all the angles that have a sine of 0.5, that happens in a few spots. You'd have your unit circle. So I just want to point out again, sine relates to my y values. So on the unit circle, where do I have y values that are 1/2? Looking around, that happens here, here, down here, and down here. All of those are technically in the same spots. If I point them out in red, then these two are in line and these two are in line. They are also both 30 degrees above and 30 degrees below my reference points. So what does that look like on this blank unit circle? You can honestly just kind of imagine where they would be at and try to draw it to the best of your ability. What we really care about is these are the 4 spots that it happens in, but the angle that we can get it there to be is what's a little more important. So if I'm starting at 0 degrees, I would point to this first one. That's one of my thetas. Then again, I'd start at 0 degrees and it would point to this one. That's another one of my angles. Again at 0 degrees, all the way around over here would be my third one. And then finally, I'm still starting at 0 degrees and make a almost full 360, but just stopping at that 330 would be my fourth angle. So as long as it's a sketch and you can kind of tell where they're at, it'll be okay. An angle that measures 4 pi over 3 radians, we want to find its exact sine. So first we want to know where 4 pi over 3 is. 4 pi over 3 on our unit circle is right over here. So whether you like to pay attention to the degree a little better or the radians in that case, it's right off our 270 mark right here. So going back, I'm just going to mark it somewhere closer to that 270 degree angle. And then how would I get there? I'd start at 0 and I'm going to point my arrow all the way to it. That would be my degree that would get me there. except we want to find the exact sine value. So far, let's kind of go and point out what that point is from our unit circle. When I have 4 pi over 3, that point corresponds to this, where I'm at negative 1/2, comma, negative root 3 over 2. So I'm going to add that in, negative 1/2, negative root 3 over 2. Remember that sine relates to the y values. So which one do I only really specifically want to see or know about? It's that negative root 3 over 2. Just the sine, just the y value. But having the unit circle is the one that lets us kind of point out what that point is in general. D says an angle with a negative cosine and a positive tangent. So let's talk about where a negative cosine or a negative x value would be in general. Again, if I'm starting at 0, 0, going left and right are my x values. If it's going to be negative, then I'm going to want to go towards the left. Now, that means I could either be up here in this quadrant or down here. Which one has a positive tangent? You got a few options. You have your unit circle, and all these circled above our points, so any of these, are the tangents. Now, if I'm only working in either this quadrant or this quadrant, I'm going to pay attention to my tangents. All of these tangents are negative. All of these tangents are positive. So that kind of is one way for me to automatically look and be able to tell. If I want a positive tangent, it would have to also be down here. So this is that quadrant that I'm really looking for. Now, a good way to put this would be that angle would be somewhere in this quadrant. And the way I'd get there is I start at 0 and I point my arrow all the way over there. And again, I'm going to put a theta to just tell me that that's a degree. Another way is tangent is y divided by x, or sine divided by cosine. And if you can, again, you'd still have your unit circle. If I look at some of my points, all of these points in this upper quadrant have at least one negative, one positive, one negative, one positive. Anytime I divide at least one negative, one positive, my answer is overall going to be negative. Now, all of these are both negative, and a positive divided by a positive or a negative divided by a negative will always give me that positive value. So that's another way. Remember that tangent is that fraction between the x and the y. So if I have two negative answers, then I'm going to end up with a positive tangent. So whether you want to look at the circles or think about what tangent is in general, you've got those two ways. All right, down here it says without using a calculator. That means you're really going to need to be able to rely on that unit circle. Otherwise, you'd be able to plug this in and it would give you an answer. So there's a reason that you're not going to have the black scientific ones rather than that blue, just kind of for operation one. But our first one here says find the sine of 60 degrees. My tip is always going to be go to that degree, and then if it's asking for sine, I want you to think about whether that's asking for the x value or the y value. So first I'm going to find 60 degrees on my unit circle. That happens over here. And I'm just going to highlight that point with it. Now it asked for sine of 60. Well, does sine relate to x's or y's? Think about that first. Since it relates to y's, this is the only thing that I care about, that root 3 over 2. And that's all you have to do. For that answer, it just equals root 3 over 2. Now I'll try the same thing for b. Find 180 degrees, and then cosine. Think about whether that relates to x or y. Since it relates to the x value, when you're at 180 degrees, tell me what that x value is. Going to 180 degrees, my x value here is that negative 1. So cosine 180 equals negative 1. Tangent's kind of nice. You don't even have to look at the point because on our unit circle, it's those that are circled on the outside. So if I'm asking you for the tangent of 225, find 225 as a degree, and then point out what that number that's circled is. So 225 is over here. The tangent that correlates with it, be a little careful. I've had some students that are mixing up these three circles. Pay attention to what it's correlating to. This one in the middle, out of my three angles, 1, 2, and 3, 225 is in the middle, so choose the tangent that's also in the middle. And that tangent would just be 1. So equals 1. The bottom ones are the same exact thing, except this time, instead of looking for that degree, you just have to look for that radian. But same exact steps. Start by looking for pi over 4. So go to that unit circle and find pi over 4. That happens right over here. And then it asks for sine. So think about whether sine asks for x's or y's. Since it asks for y's, that would be what you're looking for. Now, in this case, even if it asked for the cosine, it's still the same answer. But because I specifically was looking for sine, that's the one we're going to refer to. Cosine of 2 pi over 3, find 2 pi over 3 on the circle. So going to my circle, 2 pi over 3 is right here. And then it asks for cosine. So think about whether cosine's x or y. Since cosine is x, this is the only one that I really care to share. In that case, my answer is -1/2. Last one is 3 pi over 2. So I want to find 3 pi over 2 on my circle. That's all the way down here. And then it's asking about the tangent. So what's that circled number that relates to it? Well, in this case, it's undefined. Let's just remember where that comes from. If tangent's y divided by x, the y value here is -1, the x value is 0. Anytime I have a 0 in my denominator, your calculator is going to tell you that it is an error. So just kind of double checking that it makes sense. That being said, tangent of 3 pi over 2 is undefined. All right, there's that front side. Let's take a second to flip it over. That first question on the back side says, if an angle between 0 and 2 pi radians, so all this is really telling you, let's highlight it in yellow, is that I'm looking for an angle on the unit circle. The unit circle goes from 0 to 2 pi, and this is talking about an angle from 0 to 2 pi. If that angle has a sine of -0.5, what is its cosine? Well, first I want you to think about what sine means. Sine relates to y value. So we can kind of start this off with the sine, or the fact that it's the y value of -0.5 is at, and let's find where it's at. So we're looking for y values with that -0.5 or -1/2. I'm gonna clear my unit circle here. And then let's just look for y values that have a -1/2. Now, the first one that I see happens right here. And then the second one is right over here. Anytime you find at least one, you're going to know that the other answer is going to be in its general area, kind of right across it, maybe right above it. So look for those instead of like looking in very random spots. So in that case, that's also this one. So where does that happen? Because they said 0 to 2 pi radians, I'm going to want to give the radian answer. So it happens at 7 pi over 6 and at 11 pi over 6. Now, they wanted a little bit more, so 7 pi over 6 and 11 pi over 6. They also wanted to know the cosine at each value. So 7 pi over 6 has a cosine of, going back to our unit circle, that's just the x value. It's this -√3 over 2. So cosine is equal to -√3 over 2. And then for 11 pi over 6, that one has a cosine of, again, cosine looks for x values. So go back to your unit circle, find 11 pi over 6, and that x coordinate this time is just regular √3 over 2. I think I forgot the negative on that. Okay, and that's all they were asking for. How do I know? Use the unit circle, found where the sine was at -0.5, and then found the corresponding cosines for each of those angles. All right, the next question says rewrite each equation in graphing form. That should automatically tell me if I want to go from standard form to graphing form. I'm going to need to use completing the square. So completing the square as a reminder, rather than when I go through finding x-intercepts for standard form, I go through diamond and box. When we think complete the square, I want you to think go automatically to just our square. Why? Because we start to fill out the square and then realize what we're still missing. X squared is still x squared. With complete the square, we really like these diagonal boxes to be the same number. And the only way that you can get that to happen is by taking this 4x and cutting it in half. So that gives me 2x for each one. That puts a 2x in this box and a 2x in that box. Now let's fill out the outside of the square. The way that we multiply to x squared is x and x. And then x times 2 gives you 2x, and x times 2 gives you 2x. How do I get this last box? Well, right now it's currently at, I'm going to underline this -12, but 2 times 2 tells me that this box should be at a 4. How do I get it to be a 4? Well, I have to go from -12 all the way to a 4. That being said, what do I add in order to get that? And a different color. I'd have to add 16 to this side. And don't forget that I still have that y by itself on my left side. I'd have to add 16 to that side as well. Now I'm left with y plus 16 on the left. And then instead of even trying to rewrite this in standard form, I'm just going to write what the box gave me. One of my factors is this one up here, x plus 2. And the other factor is also x plus 2. So instead of writing x plus 2, x plus 2, I can just write x plus 2 squared. Standard form, graphing form is where I have y by itself. So subtract that 16 to the other side. And this is what we're looking at, where I have x plus 2 squared, and then the minus 16 that comes after. All we need now is, it doesn't ask us, oh, actually, yeah, it does ask us for the vertex. The vertex here is the opposite of this, and then this number just as is. So anytime I'm looking for the h value, it's always got to be the opposite. This looks like a +2. The opposite of that would be -2. And then this number is just as is. So it's a -16. So -16. Now this is a parabola, meaning it looks like this shape. So the domain for our function here is just all real numbers. It's going to continue forever and ever in both directions there. The range, though, because I have a vertex here, it happens at -2, -16. My range, paying attention to those y values, tells me that the lowest I'm ever really going to get is to that -16. So my range, I can say, are all the y values that are greater than or equal to my vertex, which is at -16. Okay, let's do the same for this one over here. We're still completing the square, so automatically go to box. I'm going to start with x squared in the top left. I want to cut this in half, so dividing it by 2 gives me 3x, -3x. And that's what goes in my 2 corner spots, -3x, -3x. And then currently I'm at a -2 for that last number. Now when I go to fill out the outside of my box, x times x is x squared. X times -3 is -3x. X times -3 is -3x. Doing -3 times -3 tells me what should be in that box, and that is a 9. So this box right over here should be a +9. How do I go from a -2 all the way to a +9? I would have to add 11 to this side. Don't forget that the y is by itself on the left side, so I'd have to also add 11 to that side. Now, when I start to go rewriting it into standard form, I have y plus 11 on the left. And like I said, don't even waste your time by trying to rewrite this into standard form, just because you're going to come up with the factors anyways. So I only really care about the outsides here, and that's x minus 3, or x minus 3 squared. Last step for graphing form is subtract that 11 to the other side. So I have x minus 3 squared minus 11. Pointing out the vertex, it's the opposite of this number. So this looks like a negative 3, meaning it should be a 3. And then it's this number as is. So just a negative 11. Same idea. This is still a parabola. So that domain should still be all real numbers. And then this time, because on my parabola, we'll use this one right over here, my vertex down here is at 3, negative 11. That means the lowest y value I'm ever going to need to hit is this negative 11. So all the y values that are possibly bigger than or exactly equal to that vertex at negative 11. The reason I know it's the y values that are bigger is because my a here is positive, meaning this parabola opens up. Obviously, if it was a parabola that opened down with a vertex up here, this sign would have to be switched. But because I know it's opening up, I know it's the y value at negative 11 and all the other ones above it. All right, we haven't done this in a little while, but find an equation for an exponential function that passes through the points 1, 2, and 3 and 0.125. Now, this one has a little asterisk, meaning you'd have a calculator. But first, I kind of want to start off with what an exponential function looks like. I want to say you have this formula on your assessment resource page, so use it to help you remember where the y, the x, the a, and the b should all go. And then automatically, I like to label each point x comma y and x comma y. That just helps me remember which one is which and helps me know that I need to set up an equation for each of them. So I'm going to start with equation 1, and I'm just going to use that 1 comma 2. Using my y equals a times b to the x, I'm only going to make my replacements for x and y from that circled point. So x should be a 1 and y should be a 2. What should that look like? If I have y equals a times b to the x, and I'm getting rid of the y and I'm making it a 2. And then I'm getting rid of the x and it's going to be a 1. That's my first equation. Now do the same to get equation 2 with this second point. Instead of y, it should be 0.125. And then a times b is just a part of my equation for now. I'm going to eventually look for those to the power of x or to the power of 3. What do you do with these two? You divide your two equations. How do you know which one to put on top? It doesn't really matter. I'm always going to recommend to put the one with the bigger exponent on top, just so you can avoid negative exponents. So here, 3 is bigger than an exponent of 1. So when I go to do that division, I'm going to put 0.125 is equal to a times b to the third power. And then I'm going to divide that by 2 is equal to a times b to the first power. Now, when I go to do that division, the left side is just as is. You do 0.125 divided by 2. So far I'm at 0.0625. And then the nice part is that I have 1a on top, 1a on bottom. That goes away. And then I'm left with b. And let's remember that when I divide, the exponents subtract. So I'm left with b to the 3 minus 1 power, or b to the second. So I almost have b by itself. I need to square root both sides here. And that gives me that b is equal to 0.25. So that's pretty much half my problem here. I'm going to erase it right now. Instead of a b, I'm going to write 0.25. Now I just need to solve for a. So what do we do here? You choose one of your equations. Out of equation 1 or equation 2, I'm going to choose equation 1, which just has simpler numbers and smaller exponents involved, and your a value. So I'm going to choose this equation up here and the b value that we just came up with. So plug in that b value in. I'd get, we'll do it off to the side here. 2 is equal to a times b to the first power. Remember that we know what b is now, so I'm just going to do a times 0.25 to the first power. Having something to the first power doesn't really do much. So that's just 2 is equal to, all right, 0.25a. And how do I get a by itself? Divide by 0.25 on both sides. Now I'd get that a is equal to actually 2 divided by 0.25. A should be equal to 8. Caught my own mistake there. Okay, so instead of an A here, it should be a 8. So this is my final answer. I came up with the A going through it that second time around, and you come up with the B value by dividing the initial 2 equations in general. Okay. These last few tell me to just solve each equation to the nearest thousands. So my goal here is to try to get the x to be by itself. Starting with our first one, the x is alone and attached to this 3, so I'm going to leave that alone entirely. How can I get that blue underlined part on its own? I want to undo this multiplying by 2. So think about how you undo multiplying by 2. You would divide by 2 on both sides. So that leaves me with 3 to the power of x is equal to 20.4. And then the only way to get an x out of an exponent is by rearranging it into a log. So log, my base here is the 3, so that's my tiny number. The y value here, the number by itself, is 20.4. And then it equals to the exponent, which in this case is x. Now, you have this symbol here telling you that you'd be able to use a calculator. Plugging this in, I can simplify that x would be around 2.74. Part B has an x to the 4th that I want to try to get isolated. That means I want to try to get x to the 4th by itself before I do anything else. So how do I undo multiplying by 3? That should be our first step. Answer to that is divide both sides by 3. Now I'm working with x to the 4th is equal to 9. I just want x, not x to the 4th. How do I undo something to the 4th power? You would take the 4th root of it. So this kind of works like our square root in the sense that it's even, meaning I'd have that plus or minus, and it would give us x is plus or minus 1.73. Part C deals with logs again, except this time I really can't do much until I rearrange it into exponential form. So my base is 5. I'm going to start with that. The exponent should be 3. And then we're equal to this part in parentheses at 2x plus 1. And then now from there I can solve. So yes, you'd have a calculator. This is also on your power sheet on your assessment resource page. That's 125 is equal to 2x plus 1. First step would be to subtract 1 from both sides. So now I'm working with 124 is equal to 2x. And then we only want x, so divide both sides by 2 to get that x is 62. All right, last one involves some log properties. So the log properties are going to be on that front side of your sheet, but that's just when I have 2 logs with specifically an addition sign between them. Their answer portions end up multiplying. So what I mean by that, I can go from 2 logs to 1 log, And then I would do essentially x times 2x. So if it's a plus sign between them or I'm adding two logs, they multiply. Vice versa, if I was subtracting two logs, they would divide. So pay close attention to your property sheet for that. This still equals 5. So now I'm working with log, and then I'm just going to rewrite this as 2x squared is equal to 5. So I'm kind of stuck with what I had in part C. I can't really do much until I rewrite it into exponential form. Some of you might say there's not a base there. I'm going to ask you to remember what base is there when one is not written for you. And that is the invisible base 10 that's always there. Now, when I go to rewrite this, I get 10 to the 5th power, and then it's equal to our 2x squared that we had. Now, actually go through and do, if you had a blue calculator, you can do 10 times 10 times 10 5 times, or you'd have your calculator for this. It gives you 100,000 is equal to 2x squared. Still want to solve for just x. So your first step should be to divide both sides by 2. Got x squared is equal to 50,000. And then I just want x. So how do I undo that? Square root both sides. And x is 233.61. Now I want to point out that because it's a square root, and anytime I take a square root, it's really the positive or negative version. But because I'm working with logs, I have to be really cautious and look for extraneous values. In this case, the positive is the only one that works, because if I were to make this x right here a negative 233.61, then I'd get an error. I can never have a log and then a negative number in that answer portion. So this negative 233.61, you can make a note, is extraneous. All right, that's about it for those first 2 pages. There will be another video for the last page, front and back.